here at the University of Sydney in person and all our audience online as well. I would start with the acknowledgement of the country. We want to acknowledge the traditional owners of the lands on which, in particular, Sydney Uni tonight is located, the Gadigal people of the Eora Nation, and we pay our respect to the knowledge embedded forever within the Aboriginal custodianship of country. Tonight, it's my pleasure to have Dr. Matt Moores from University of Wollongong. Matt completed his PhD in 2015 at QT under the supervision of Kerry Mangerson and Fiona Harden. He then moved to the UK for a postdoctoral position at the Department of Statistics of the University of Warwick, first under the supervision of Mark Girolami, and then under the supervision of David Firth. He joined the University of Wollongong in 2018 as a lecturer in statistical science. And in 2021, he was awarded the title of docent in computational statistics in Finland. Matt's research interests include MCMC and SMC algorithms, and he worked thoroughly on spectroscopy, which is the topic of his talk today, with the title Bayesian analysis from spectroscopy. So before starting the seminar, I would ask all the people online to mute their microphone to have a better recording. And I also recall that this seminar is recorded for members of the SSA. So thank you very much, Matt, to join us tonight. And the floor is yours.
Thank you. Thanks very much, Clara and Gordana, for inviting me to come along and give a talk to everybody tonight. And I also want to thank my colleagues at Lappeenranta University of Technology in Finland, Warwick and Strathclyde, and the Turing Institute in the UK, who all contributed to this work. So tonight I'm going to explain what Raman spectroscopy is, and I'm going to introduce a statistical model for this type of data, as well as some Bayesian priors to go along with the parameters of this model. And then I'm going to spend a bit of time sort of explaining how, using SMC, I fit the model to the observed data, and in particular using this R package SERS-Bayes that's available on CRAN. And then I'm going to talk about some new work that we just put on arXiv this year, where we're detecting the peaks in a spectrum where we don't have very much prior information available. And that's using a combination of deconvolution as well as Poisson process to then smooth the results of that Fourier analysis. And then at the end, I will give a bit of an update on where I'm at with the Mars 2020 project. So the latest robot to land on Mars, or pair of robots rather, because there's a helicopter flying around on Mars now, as well as the Perseverance rover. They kind of work as a team. And I'm also going to talk about some data collected on Earth that is similar to the data from Mars, but where we can actually validate our method using that data. So how Raman spectroscopy works is that light interacts with matter, and some of that light scatters and loses energy. In this case, what we have is a laser. So the light coming in is all the same wavelength, And then it reflects off this mirror, which is designed to reflect only the green light, and it's going to let through any of the scattered light which comes through at different wavelengths. Because what happens when the photons lose energy is that they're then redshifted, and so all of that redshifted light then hits the spectrometer and gets measured, whereas all of the light that is still green reflecting back off. So there's something called Rayleigh scattering, which scatters off at the same frequency that it goes in. And that's a much stronger scattering. Most photons Rayleigh scatter. And so we want to get rid of those so we can actually have a chance of measuring this Raman scattering. So this is a Raman spectrum. And on the horizontal axis, these are in wave numbers, and this is how much the photons have been redshifted. The peaks in this signal correspond to atomic bonds in the molecule that that light has interacted with. And so this gives us a unique spectral signature for this molecule, which happens to be methanol. So methanol is toxic to humans. And so, for example, if we have beverages for human consumption, we want to make sure that there aren't detectable levels of methanol, which is a byproduct of the production of alcohol that we want to make sure that we get rid of. Now, we know the locations roughly of these 4 peaks because we know the structure of this molecule. So if we know how the molecule is put together, we can then predict where the peaks roughly should be. And because we're using Bayesian inference, roughly is good enough because that gives us a prior distribution based on the atomic structure that we can then fit to the data and find out where the peaks actually are in our sample. Now, you might have noticed in that previous slide that the vertical axis didn't start at 0. And there was kind of a trend in the data. And we want to get rid of that, what's called a baseline, before we analyze our spectrum. Because that doesn't come from Raman scattering. It comes from fluorescence and background light and other things. So there's various methods, deterministic methods for estimating this baseline. But what all these methods share in common is that they have different models for the baseline, but they don't actually model the peaks at all. And what we would like to do is a model-based analysis where we consider a baseline more probable if it jointly gives us a higher probability that the peaks also match the data that we've observed. Because in fact, the peaks are really the thing that we're interested in. That's this spectral signature S here. And the baseline, we're basically going to remove. And of course, we're also going to assume that there's some additive noise left over that isn't modeled by either of these other 2 things. The other thing to note here, the title of this slide is Functional Data Analysis, because what we have is a discretized signal that we observe, but our underlying processes are both continuous functions. So both the baseline and the peaks are continuous, but we only observe them at discrete points. The main thing that we know about the baseline that seems to be true of pretty much every baseline in Raman spectroscopy is that the baseline tends to be very smooth and slowly varying. And so the model that I use for the baseline is a penalized cubic spline. And this has the advantage that we can put a conjugate prior on the parameters of this spline, and then our conditional posterior for the baseline will be available in closed form. And this type of conditional linear model has a lot of advantages, especially when we're doing our analysis using sequential Monte Carlo, as I'll explain further along. The spectral signature, which is the main thing of scientific interest, is modeled using 3 parameters. The locations of the peaks, which, as I mentioned, for methanol, we roughly know what those locations should be. Also, the amplitudes of the peaks, and these are interesting because the amplitude is proportional to the concentration. So we can not only detect the presence or absence of methanol, we can estimate what percentage of methanol is in the substance that we're measuring. The last parameter is the scale parameter of this function, and this controls how wide the peaks are. So I'll give some specific examples. The easiest model to use, and probably the one that most statisticians would be familiar with, is we can model these peaks using an unnormalized Gaussian PDF function, basically. And then the scale parameter is, of course, just the standard deviation. But that gives us something physically meaningful for the chemists, because using this scale parameter, we can then calculate posterior credible intervals and so on for what's called the full width at half maximum. In other words, if you take a point halfway up the peak, then how wide is that peak? And this is something that chemists understand very well, and it's usually a property of the spectrometer. It's something that comes about as a property of how you're actually measuring the spectrum. The more realistic function that we tend to use is known as a Lorentzian broadening function. Statisticians are more familiar with this as the Cauchy PDF. So this is just an unnormalized Cauchy. And of course, this is going to give us very, very heavy tails between all of our functions, which is important to take account of in spectroscopy, because if you want to measure, for example, the height of this peak, you need to take into consideration that it's right next door to these other 2 peaks that are overlapping with it, even though you can't actually observe where they overlap. There's a third type of function called a Voigt function that is also supported in the R package, and it's actually a convolution between a Lorentzian and a Gaussian. So it's kind of in between. So it's not as heavy as a Cauchy and not as light-tailed as a Gaussian. And that then gives us an extra parameter, the width of the tails that we can estimate. So we have our 4 peak locations, and our prior for the locations of the peaks is just going to be a normal distribution centered at the location that we know from our molecular analysis, and then with some kind of uncertainty associated with that. For the scale parameters, this prior I've been using, I think, for about 15 years now, and it's been very reliable in Raman spectroscopy. As I mentioned, the broadening is kind of a property of the spectrometer that you're using. And so I've done some work with X-ray spectroscopy and also with radio waves. And this broadening parameter, you kind of need to get a prior for that for each type of spectroscopy that you're using. But this prior works very well for Raman. The amplitudes, however, are a different story, and it's kind of a headache to set a robust enough prior for the amplitudes that isn't going to fail on some subset of all of the possible Raman spectra. This prior that I've outlined here, the truncated normal, we only really use that now if we've got very good prior information on the spectral signature. If we're analyzing a new molecule for the first time, we'll tend to either use just a uniform prior, or we'll use an exponential prior that kind of penalizes very large peaks. In some circumstances, depending on what the baseline is doing, how wiggly it is, and so on, sometimes an exponential prior here can be very useful. So how sequential Monte Carlo works, if you haven't seen this algorithm before, and this is a particular form of algorithm, it's very popular in signal processing in a whole ton of different applications. The specific type of algorithm I'm using here is the likelihood tempering SMC that was introduced by Pierre Del Moral and colleagues. So at time 0, we're going to initialize what are called particles in SMC, but are really just our samples, our parameter values. And we're going to sample all of our parameters from those priors that I just showed you. And then we have these important sampling weights. And under the assumption that we can sample from these priors, then all our weights are just 1 over the number of particles that we have. So everything's just equally weighted to begin with. Then we're going to choose a power kappa that we're going to raise our likelihood function to that power. And kappa is going to start at 0 when we're at the prior, and it's going to be equal to 1 when we get to the posterior. And the nice thing that I really like about SMC is that it's possible to choose this kappa adaptively. And that's quite important because you don't just want to do like increase kappa by 0.1 at every SMC iteration, because you need to take very, very small steps when you first introduce the likelihood. But then once you've sort of warmed things up, you can take much bigger steps. And so doing that adaptively is very beneficial and helps the SMC actually converge. We also need to be concerned with this effective sample size. So this reweighting step is just important sampling. So our proposal distribution is our prior. And then we're going to update all of our importance weights based on our likelihood at each iteration, or some power of our likelihood. But we need to monitor this effective sample size, because what can happen if we take too big of a step is that our effective sample size will just go to 0 very, very quickly. So what we do to avoid that is that we actually resample our particles from the current distribution of our SMC. And so we do that just by we normalize these weights by dividing by the total. So then our weights are between 0 and 1. And then we resample using our weights as our probabilities of resampling our particles. And then there's a final step, because this resampling is going to duplicate the particles that have the highest probability. And we don't really want to have duplicates, especially if we have a continuous parameter space. And so we take some MCMC steps after we've resampled to try and get rid of those duplicate parameter values. So this is what kappa looks like in a typical SMC from this R package. So here we start at the prior, we start at 0. Then every iteration we increase kappa, starting very, very baby steps to begin with, but then we speed up as we get closer to the posterior, we can take bigger jumps. And we choose, at every iteration, we choose the new kappa adaptively. I mentioned the importance of effective sample size. So what happens every time we increase kappa, our effective sample size goes down. And so that's what you see happening here. Every iteration, our effective sample size is dropping. Then when we do a resampling step and MCMC steps, our effective sample size comes back healthy again. And then, of course, we start increasing kappa again, and it starts going back down again. So that gives us this characteristic seesaw shape that we get in SMC. The resampling itself, so the simplest type of resampling is multinomial. So we just take those weights and normalize them and then do multinomial where all of our probabilities are just the weights themselves. That's very easy to implement, but unfortunately it also has the highest variance of any of these 4 methods. So anything other than purely random resampling generally tends to outperform the simple random resampling. In our R package, we use residual resampling. And we actually do this in parallel and in place. So we only overwrite the particles that we're throwing away anyway. So we reuse the memory and do everything with multiple threads, which is another big advantage of SMC. And so Lawrence Murray and colleagues have a JCGS paper that explains how to do this resampling in place and in parallel. And this gives a big speed up to, as well as increasing the memory efficiency of SMC algorithms. I mentioned that we had a conjugate prior on the coefficients of our spline, of our penalized spline. And this enables us to do something that in SMC is known as a type of Rao-Blackwellization. So what we do is we're effectively integrating out all of our spline coefficients as well as our noise parameter from the model, which then reduces the size of the parameter space that we're trying to do Monte Carlo inference with. So we don't actually estimate the baseline as we're fitting the model. We're estimating the peaks and we're integrating out the baseline because that then is just a multivariate normal posterior distribution. So what can go wrong? SMC is a great algorithm and I use it everywhere I can, but it does have its flaws. And in particular, if you don't start with enough particles that you've sampled from the prior at the beginning, or if you don't do enough MCMC steps after you've resampled, both of those things can combine to result in all of your particle weights concentrating on one single particle. And so you start out with an effective sample size of 2000 and you end up with an effective sample size of 1 because you've got one particle that has non-zero probability and all of the others are zero. And this can happen just in normal importance sampling as well, if there's too much distance between your proposal distribution and your target. And it sort of has a cumulative effect in SMC because we are resampling and doing MCMC moves. So we're kind of keeping things alive for a while, but in the end, we fall over. So other than this, SMC is great because when it does converge, it tells you it's finished. So unlike normal MCMC where there's kind of no sufficiently long time to run an MCMC sampler, more samples are always going to reduce your Monte Carlo error and so on. SMC, you kind of decide up front how much computational effort you're going to spend, and then it runs everything adaptively and lets you know when it's done. And you can have RStudio play a song or something when your SMC has converged, which is good fun. So this is the R package. I won't go into detail of all the syntax. I will mention this other R package called Hyperspec, which is very useful if you're working with chemists, because they have all of these weird file formats that they like to keep their data in, which is still definitely preferable to recording spectra in Excel spreadsheets. So we like to say, no, don't give it to me in Excel, please just give me the raw data. And then R has this Hyperspec library that's really good at reading that data into R, turning it into a matrix so that then, this is our horizontal axis, this is our Raman spectrum, and then we just pass in the priors as a big list of hyperparameters for all of those distributions that you saw earlier. So at last we arrive at our posterior distribution when kappa equals 1. Here what I'm showing are samples from the continuous function for the spectral signature, which is in sort of bluey green, as well as the continuous function for the baseline. Even though we integrate out the baseline, because that posterior is available in closed form, you can always run a Gibbs sampler conditional on the rest of the parameters to give you your baseline samples at the end. There's a bit of a hiccup with this one though, because we can kind of see that this peak isn't quite in the right position, and we seem to be missing a peak over here maybe, because our baseline otherwise is quite regular and has taken a bit of a detour down here where there seems to be kind of model data mismatch in this distribution. So this is what our nice continuous spectral signature looks like when we have 4 peaks. So remember this because we're going to reanalyze this data using the method in our new paper to try and get better fit to the data that we've observed. So what do we do when we don't have the structure of a molecule that we've analyzed, or say in this case, we've got a prior that should have worked, but seems to be missing some of the key information in the spectrum? Then another approach is deconvolution, where we can represent our spectral signature here as the convolution of our Lorentzian function or our Gaussian, for example, and a weighted sum of Dirac delta functions. So what this gives us is in one half of this equation, we've got our peak locations and our amplitudes. The only thing we sacrifice by doing this is this equation is slightly wrong because you can only have one scale parameter that's shared by all of the peaks. To be able to take this outside the sum like this, this actually has to be a fixed parameter that's equal across all of the peaks in the spectrum. But in practice, this doesn't matter too much. And we can, using importance sampling, kind of fix that up at the end. So this is our convolution. And then what we want to do is deconvolve our signal. And we do that by taking the Fourier transform of our observed signal and dividing it by the Fourier transform of our Lorentzian or Gaussian function. And so that then, because convolution in our original domain is multiplication in the Fourier domain. So if we divide two Fourier transforms by each other, we're kind of deconvolving in frequency space, and then we take the inverse Fourier transform to come back to our original domain again and give us our nice delta functions. There's kind of a problem with doing this though, because although this is our nice continuous, it's written in terms of our nice continuous Fourier transform. Of course, what we do in practice is the fast Fourier transform, because our data here are actually discretized already. And there's a couple of other steps in here as well. In particular, we're going to truncate our Fourier representation at a finite number of frequencies. And part of the reason that we want to do that is we want to get rid of the additive noise, which is the highest frequency component. So we pick a truncation level M, and we're going to say anything with a higher frequency than that M is noise that we throw away. So then what we end up is the product of our delta functions and our Lorentzian kernel. And then the kernel part we don't really need anymore. We can just use those delta functions, maybe. In practice, what we get after all of this is this signal in orange. So this is when we do the inverse DFT and come back to our original domain that we started with. And we've got a few problems here. So we have what are known as ringing artifacts in this signal, where we kind of have peaks that sort of echo off to infinity. We also have, so this is 0 for the Fourier transform, and we have negative peaks now. And there's not really anything that we can do about that. At least we don't have imaginary peaks, they're all real numbers. So it could be worse, I suppose, but this is still not good. And there was something else. Oh yes, peak splitting. So this Fourier way of analyzing the signal tends to give us more peaks than are really there, because it's still, even though we've got that truncation M, it still kind of can pick up on random noise and decide that that's a peak when it really isn't. So what tends to happen is, although in the real data there might only be one peak, it might say there's 2 or 3 or 4 peaks in kind of that general location. So what all of this means is we need to apply some smoothing and regularization to the output from this Fourier deconvolution. And that's kind of good news for us, because Bayesian statistics is really good at smoothing and regularizing very weird signals in data. The approach that we take is using this Poisson point process. So I won't go through this in too much depth, but essentially what we're going to do is partition our domain into these disjoint subsets. And then the number of peaks inside each of these partitions are going to be independent random variables so that we get a nice form for our likelihood. And in fact, what we're going to have is that the expected number of peaks inside one of these partitions is going to be given by this function, which is known as the intensity measure. So this is our lambda parameter of our Poisson distribution. It's just the mean of our Poisson. To turn this into a log Gaussian Cox process, we need the derivative of this capital lambda, which I'm just going to call lowercase lambda. And this is known as the intensity function. It's a bit like a PDF, but it isn't. The reason for that is if capital lambda of S was equal to 1, then we would have a PDF because it'd integrate to 1. That's really the only thing that it lacks. So we can have more than one peak, as you've seen, in the entire spectrum. And so that means little lambda is going to integrate to some number, most of the time is going to be bigger than 1. So then we have what's called a doubly stochastic point process, which means that we have a Poisson process that I explained on the previous slide, but that Poisson, those Poisson counts then depend on this continuous Gaussian process. So the log of little lambda is a GP that has some kind of variance covariance function. Typically, this would be something like a Matern function. So we control the amount of smoothness that we apply by choosing what covariance function, and then we can infer these parameters theta from the data. So this is what it looks like. Now in blue, I've kind of switched color schemes here. In blue is my Dirac delta functions that I got from my inverse Fourier transform. Then in orange here now is my Gaussian process, which gives me a smooth version of these discrete functions. And this shows in orange, this is my Gaussian process, the mean of my Gaussian process against our original Raman spectrum data. And so we need to still apply a little bit of thresholding here. Depending on how zoomed in you are, you can see there's sort of some wiggliness going on in the middle here that we kind of want to threshold out. But these three peaks that we know from our molecular structure, we're finding using our log Gaussian Cox process. Over here, however, where we only had one peak originally, and we thought maybe we might have wanted two peaks, it's saying that it wants to have 6 peaks over here to model this thing that kind of looks like a mountain. And so that's each peak that I'm talking about here is a local maximum of this Gaussian process. And the derivative of a Gaussian process with a Matern covariance is also a Gaussian process. And so it's quite easy to figure out where these peaks are from this output. Certainly much easier than what we got originally from our Fourier analysis. And so then we use that to fit our same model to the data, but now we have 9 peaks instead of only 4. And we've got much better fit of our model to the data. It turns out we're probably slightly overfitting actually, because this looks like we've still got a bit of residual peak splitting going on, where maybe this is actually 3 peaks rather than 3 pairs of peaks in this data. This is still okay because we can have an over-parameterized model and it behaves reasonably well in setting the amplitudes of those peaks very close to 0. So this then still gives us quite a good estimate of our spectral signature that actually isn't too different to what we would get if we use 6 peaks instead of 9. So now let's talk about some real data. This Perseverance rover was launched in 2020. It was originally known as the Mars 2020 mission, and it successfully parachuted down to the surface of Mars in February last year. And it's still running around this Jezero crater, which was selected as the landing site. And the first public release of data was in August of last year for the first 90 days that the rover was on Mars. And so not only the Raman spectroscopy, but all of the measurements and photos that the rover has taken for those 3 months are available on the NASA website freely to download. One of the Raman spectroscopers' spectroscopes on this Mars rover is in its arm, and the other one is in sort of the head part of the rover. So this is what sits inside its head. And you can kind of recognize, so the light comes in here. This is a mirror that is going to filter out light that's the same color as the laser that it fired at whatever it's measuring. And that kind of turns a corner and ends up with a CCD detector, which is just a digital camera. And so this is how we measure this Raman spectrum on Mars. And you can see this is a ballpoint pen for scale. So very light, very compact, very efficient. And in fact, there are also handheld Raman spectrometers on the market where you can do things like analyze, like go into a shop and analyze whether, for example, say that they claim that something is like 80% proof, then you can verify that it actually is. And do that type of, with various foods, verify that it is actually what it says on the label. The idea of this spectroscopy on Mars, what it's looking for, is for signs of life. So they're really focused on detecting organic carbon in any of the samples that the rover finds. And there's a plan in the future that the rover is going to actually collect some physical samples and eventually will bring those samples back to Earth. So at some point, we will be able to evaluate against a ground truth of the samples that we bring back. But of course, there's only, I think there's mainly only 9 samples that it's going to take that it are planned to return to Earth. And so it needs to prioritize based on things like total organic carbon, which samples it's going to keep and try and sort of archive for eventual retrieval and return to Earth. So at the moment, and probably for many decades to come, we won't really be able to validate our method against any kind of known ground truth. However, what we do have is 10 samples that were collected in Utah at what's called a Mars analog site. So it's out in the desert in Utah. The rocks in that desert are very similar to the types of rocks that would be found on Mars. But because it's on Earth, we know that there are going to be signs of life, because almost everywhere you look on this planet, there's some living creature, no matter how small, or the fossilized remains of living creatures, maybe even from millions of years ago. The types of spectrometers that they used in this study match the two spectrometers that are on Mars right now. And so this gives us representative data. The goal here is to estimate the composition of each sample and decide whether it's biologically meaningful or whether it's just a boring rock. Now, in their paper that originally published this data, they thought they had 4 different peaks, which corresponded to 4 different elements that they thought were in this sample. And one of those 4 turned out to be organic. However, there's more going on in this signal, particularly over here, in terms of things that really kind of look like peaks in the signal. And so what we'd like to do is reanalyze this data using our Bayesian method and see if those peaks are physically meaningful or if they're just artifacts in the signal. This one over here, we actually know is caused by gamma radiation. So this is a cosmic ray that's hit our digital camera and burnt out one of the pixels in that camera. That's why the shape of this peak, even the positive ones, it's very, very narrow down on a single frequency, which then corresponds to the frequency of that gamma ray that collided with it. So this is kind of a known problem. Whenever you're doing spectroscopy, there's some chance that a gamma ray is going to mess up your experiment. And in fact, on Mars, which has much less atmosphere than Earth, probably there's an even higher chance. So how we analyze this signal is we now have more than one different, what I call N member, but more than one type of molecule in our sample. And so we have a library of spectral signatures that we want to match against. Some of those things will be rocks and some of those things will be organic things that we're interested in. And we can still do our baseline trick that we used earlier to integrate out the baseline and the noise. So here's an example of a rock that, if you're a geologist, is probably exciting, but not so much if you're an astrobiologist. This is our reference spectrum that we get from that rough database. So it has a gigantic collection of Raman spectroscopy of rocks. So we can use this to train our model, figure out how many peaks there are, remove the baseline, and then get our spectral signature for gypsum. So if we detect this in our sample, whether that's on Mars or in Utah, we know that that rock is gypsum. The more exciting one is beta carotene, which is one of the organic molecules that they did detect in Utah. So in particular, we've got these 2 peaks here, which were visible in that observed spectrum from Utah. So we've got 3 replicates here. I'm just going to take one of them for now, estimate our baseline, and that then gives us our spectral signature for beta carotene, which is the thing where we say, great, this is a sample we want to bring back to Earth. So in further work, we're still building this library of spectral signatures, which takes a fair while, as you might expect, because we've got to run SMC for every one of these. We're still sort of playing around with what priors and what algorithm we should use to sample these concentrations. So we're looking at things like spike and slab priors, because if there's no organic molecules, then it should say that there's a concentration of 0. And similarly, things like a slice sampler to actually explore that posterior distribution. There's an additional hiccup that I didn't talk about tonight, which is the spectral signatures on Mars don't entirely match up with what you see on Earth, because the Martian atmosphere is not at standard temperature and pressure. In fact, it's incredibly cold, very little atmospheric pressure at all, and that then affects what you observe when you do spectroscopy. And that basically concludes my talk, and I'm happy to take questions.
Thank you very much, Matt, for a great talk. It was super interesting. Is there any question from the audience? Yep. Welcome.
I don't know much about SMC. Oh, sorry. Thank you. I don't know much about SMC, but I was kind of curious about the residual sampling versus the multinomial. Could you talk about that?
The different resampling schemes.
Yeah, you said
you
kind of said there are 4,
so
and you then
there's a lot of very theoretical papers that go into proving that. So what these 3 schemes have in common is that there's some deterministic step where, for example, say that you've got a particle that has 3 times as much probability as any of the others. You want to make sure that you keep that one. Whereas if you're doing pure multinomial resampling and you've got 2,000 particles, even though all the other particles individually have very low probability, it's more likely you're going to pick one of those that have low probability than actually the high probability one that's actually a very good parameter value with a high likelihood. So that's essentially the idea behind these. And so residual resampling, basically anything that has a probability over 1/n, you're going to keep. And then you subtract that from all of those weights, and then you resample what's left over. So you still, there's a random part, you still do the multinomial thing, but you only do it on sort of the leftover probability. And that then means that things that have more than kind of a threshold survive to the following generation. So it's got a lot in common with genetic algorithms, the way that SMC kind of works. And that's certainly one of the things. So we kind of bias the resampling, but then you can prove that your posterior distribution is still targeting the correct distribution, even though we're doing this kind of deterministic thing at that point.
Thank you.
Is there any other question? Oh, maybe there is a question from the
chat. Yes,
chat.
looks like somebody's.
So Hanling say, thanks, Matt. Derivative of a function model spike, integration makes a process smooth. How to choose the cutoff between high and low frequencies in the Fourier transformation?
Yeah, that's a really good question. So there's certainly still some things in this algorithm that are not purely automatic. And the threshold when you decide something's just white noise is something that has to be pre-specified upfront. And then similarly, when we get our Gaussian process and we want to filter out those tiny little bumps, the low threshold there that you want to filter things out is another tuning parameter that needs to be decided up front. It's kind of a bit easier there because what you have is a Poisson distribution on the number of peaks. So similar to this resampling idea, obviously the biggest peak, you know that one you want to keep, but how many of the others you actually resample is kind of a bit dependent on tuning.
I may have a question related to this, I think. So when you had the picture on
Of the Gaussian process?
Yes, like when you are estimating the function. Yes. When it's already like, I think after this. Just after. Yeah, this one.
Mm-hmm.
So, and you said that, like the fit of this one was better than the fit when not using Gaussian processes. So
yeah,
how do you define this fit? I mean, visually I can
so
say.
this is the, yeah, so what happens is, so we have this assumption of additive white noise. And so when you subtract out your spectral signature and your baseline, what you have left should have constant variance, independence, all the usual kind of regression assumptions. And what we've got here is not only a big difference between our data and our model, but it's all correlated with each other. So it's like highly correlated, it's all biased in the same direction. So it's not a mean zero error anymore. It's kind of like you've got all of this mean zero error. And then when you get here, you've got all of these things where the residuals kind of take this huge long correlated detour and then come back to zero again. And then they might take a detour in the other direction. And that's kind of a sign that there's some mismatch between model and data.
Okay. Can you just conclude? Oh, there is another question.
Okay.
Because very quickly, so my question was, you said that like there were 9 peaks estimated?
In the new version, there's
So,
only 4 here based on the structure. So what we would need to do is go back to the physicists and chemists and say, does 9 peak, are the 9 peaks physically interpretable?
Okay.
Because in this case, we know the molecular structure. So we can actually do the ground truth of, do these peaks exist or are they just artifacts of our
Because my question was, so can you improve the fit actually with more peaks, even if they're not interpretable? So can you statistically improve the fit?
For sure. I mean, you know, there's theorems. If you throw a million functions at this, you'll perfectly fit the observed data.
Yeah.
So there is a point where you're definitely overfitting.
Thanks, Matt. Very interesting. An intriguing thing about going to modelling talks is that if they're non-Bayesian, the Bayesian models aren't mentioned, and if they're Bayesian, you don't hear anything about non-Bayesian modelling. Has there been any good work done on using non-Bayesian approaches to these problems?
It's very hard to get this likelihood to be identifiable if you don't regularize everything. And so there's an issue, and I kind of mentioned on my last slide, this ALPS algorithm that I'm working on for multimodal distributions. So if you're not looking at the posterior, if you're just looking at the likelihood of the data by itself, then this model is highly non-identifiable. both because your peaks, so similar to like a mixture model, your identity of your peaks your likelihood is invariant to permutation of the labels of all of your peaks. So if you don't have a prior on the peak locations, and these peaks can wander everywhere, they'll just swap over, and you'll get a factorial number of local modes in your likelihood function for the number of peaks that are in your spectrum.
That presupposes that you use parametric modeling.
Right. So the reason that I've gone for a parametric model rather than something like wavelet analysis, and I think this actually relates to Clara's comment as well about, well, if 9 peaks is a better fit than 6, why don't you just use 100 peaks, for example? And that's much closer to something like a wavelet analysis, where you pick a form of wavelet that kind of looks like a peak, and then you fit your spectrum, and then you kind of, similar to what I have with the Fourier analysis, you've got to do some kind of processing and thresholding to figure out which wavelet coefficients are really peaks and which are baseline and which are just noise. So the wavelet itself doesn't separate those 3 things from each other, but you could sort of post-process the wavelets to figure that out.
Let's see if there is another question.
Yeah, there was another one in the chat. Thanks, Noel. In the resampling, is it clear in advance what to stratify on, or is it done adaptively? So I guess that's why there are, so those 4 are not the only resampling algorithms. They're the 4 that have the most theoretical proofs written about them. So we at least know that if we use one of these 4, we're pretty confident that we're not going to mess up our inference. So I have seen SMC talks where they've done weird things like, instead of resampling and then doing MCMC to maintain the target distribution, they'll just jitter the points with like a uniform kernel after they've resampled. And the problem then is the target distribution of that algorithm is no longer the one that the algorithm was originally designed. So you do have to be quite careful with this resampling step, similarly with like sequential importance sampling with resampling. The resampling part is the thing that can mess things up. And even so, a lot of theoretical analysis, it's a lot easier to prove that importance sampling works with no resampling step. To actually get a proof that kind of survives past that random resampling is quite tough.
Okay, so we are already over time, and so I would let further discussion for the dinner. But thank you very much, Matt, for being here and to give an amazing talk. And thank you all of you who came here tonight and online as well. So our next seminar is on the 3rd of August. And we'll circulate more information soon. So thank you very much for coming, and have a good night, everyone.